Okay, so recording. All right, so in short, it's the content that we're going to go over today is stuff that you, if you took BASIC, you would have seen in BASIC. So it's electron configuration. Because the way that that is taught for the, for the way that that is taught, or at least the way I like to teach it, it's really hard to do with something like PowerPoint, where I can't actually focus on drawing things in as we go along. So the videos that I've produced are where that instruction is going to be. They're really not going to be part of this lecture. I'll make mention of it, I'll draw some attention to it, but for the most part, electron configuration is going to be covered in the video. I think it's the second of the two electron configuration videos, goes into some of the shortcuts too. So you're going to want to take a look at those for instruction on that if you are not familiar with electron configuration. Okay? So today we're going to touch on a little bit of that, and then we'll go into periodicity and how things like the quantum model inform our modern view of the periodic table. So let me go ahead and start to share the screen. And I am recording. Okay, good. So I will share my screen. Okay. Minimize. Laser point. Okay, so quantum overview, because it's not like a stop of quantum and a start of this other stuff. It's all very related. So we're going to do a little bit of like relationships between the two. We'll go into orbitals in a little more detail, how electrons go into orbitals, and then how that informs the way that the periodic table is ultimately organized, as Mendeleev sort of pointed out to us. And don't forget, you have a quiz that is currently open, closing tomorrow at 2. I sent you guys the content that you can expect on that. The extra credit is due tomorrow at 11:59, and then the homework is due on Sunday, 11:59. So all of those things coming up. So quantum. All right, so the basic summary of this, we have two ways of thinking about atoms. The first is the Bohr model, which is, while fundamentally incorrect, not necessarily the worst way to think about atoms. And if most people walked around thinking about atoms in the Bohr model, I'd be quite happy. But it's a classical treatment of electrons, meaning that electrons are going around a nucleus at a certain speed so they don't go crashing into it. It's like planets orbiting the sun. It's based on that kind of Newtonian thing. And the electrons in these orbits that are based on a certain size. And so you can have an orbit that is this big or an orbit that is like this much bigger, but you can't have one in between those two sizes. There are allowed orbits of the right size, and then there are everything else is a disallowed orbit. That requires us to treat these things deterministically, meaning if we know where an electron is, we know where it's going to be. And that is a bit of a problem. So, but regardless of the model that we're working with, the Bohr model, one of the things that we do know is that electrons do move around in these orbits, and that corresponds with them absorbing. So if we have an electron and it absorbs some energy, it moves to an outer orbit, and then when it gives back that energy going back to an inner orbit, light is given off. So all that jives with Bohr model, and remember, he was able to model the hydrogen atom with his model. The quantum model is one that uses probability, and that is the key word here, probability, to describe the potential location of electrons in atoms. We can actually even use it for atoms, but atoms get kind of big. So the electrons exist in 3D volumes of space, and those are referred to as orbitals. So the orbitals that we talked about, S-shape, P-shape, D-shape, and F-shape, they are all 3D probability maps of where you might find an electron in an atom. Absorption and emission, they deal with electrons moving between those orbitals. And this, unlike the Bohr model, is a strong predictor of atomic properties throughout the periodic table. So it's not restricted to single electron atoms like the Bohr model is. The quantum model seems to work for almost everything. However, because it's not derived from first principles, if a better model comes along, we'll start using that one. So to go back to orbitals for a second, we saw that when you solve Schrödinger's equation, there are these 3 orbitals we went over last time, and then I'm adding this last one here. So these 3 that we went over last time, N, that's a kind of a cursive L, and then M sub L, and this is the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. And then this other one over here is the magnetic spin quantum number. This can have integer values of 1, 2, 3, and so on. Which means that L can have values of 0, 1, 2, 3, and so on, as high as n-1. M sub L can have values of negative L up to 0, up to positive L, so whatever the value of L is, negative that, integers up to 0, and then integers up to positive L. M sub s has values of plus and minus 1/2. And those are the only two values it can possibly have. Now what this refers to is the spin about an axis. So if you can imagine an electron is sort of a circular thing, there's an axis for that circular thing and it spins one way around the axis or the other. So that is what we're referring to with this. So each orbital can hold one negative spin and one positive spin, or one clockwise spin, one counterclockwise spin, however it is you want to think about it. And remember, these things tell us something about the orbitals. So n is the size and the energy, L tells us about the shape, S, P, D, or F. M sub L tells us about its orientation in space, and M sub L tells us about the spin about its axis. So one important relationship for us to think about is if I'm dealing with a certain energy level, what does that tell me about where electrons can be? So if I'm in the first energy level, where n is equal to 1, I only have one kind of orbital, the S-shaped orbital. And that's the number of possible orbitals I have, 1. And it can hold up to 2 electrons. Each orbital can hold up to 2 electrons. Excuse me. A second energy level will contain 2 kinds of orbitals, S and P. There is 1 S and 3 Ps for a total of 4 possible orbitals. And 2 electrons fitting into each one will take us to 8. The third energy level, S, P, and D, contain 1, 3, and 5 orbitals respectively, so that adds up to 9. 2 electrons in each one of them goes up to 18. So the third energy level, I can hold up to 18 electrons. Fourth energy level contains S, P, D, and F electrons, which means 1, 3, 5, and 7 electrons in each one of those respectively. So 16 is the total possible. And this should actually be 32, not 36. How did I get that wrong? This will be changed. This is 32. So this should be there. And here's the reason for it. If I have n as my energy level, so some number n, the formula I would figure out for this is how many kinds of orbitals can I have? N. So if this number is 5, this number is 5. This number is 6, this number is 6. How many possible orbitals could that mean? The square of n. All right, so when it was 4, it's 16. When it's 3, it's 9. So whatever n is squared, and then 2n squared is this. So I just ended up blindly doubling that one. I should have doubled this number. So that'll be 32, not 36. Look for that change in the notes when you guys see it again. So when we fill these orbitals, an atom like lithium has 3 electrons, 2 of which are in the first energy level in an S-shaped orbital. One of them is an S-shaped orbital of the second energy level, so it gets the electron configuration. 1s2, 2s1, and if we take these two numbers here and add them up, 2 and 1, that's the total number of electrons that we have here. And you see the same thing with beryllium. 2 in the second level S-shaped orbital, 2 in the first level S-shaped orbital, that's a total of 4. There are 4 electrons in beryllium. When it comes time to add a 5th electron, for boron, there's no room in the first or second energy level, so it goes to the P's of the second energy level. So we've got a total of 5 electrons here, adding up to 5 for boron. 1s2, 2s2, 2p1. Carbon, if we have a place where we can put an electron, it's either going to go in the second spot that's available here, or it's going to go 1 over, and it prefers to go 1 over. This is referred to as Hund's rule, which I'll talk about in a minute. But these p-shaped orbitals are degenerate, and so basically everybody wants their own room first before they double up. Right? It's like seats on a bus. If I get on a bus and there are no one in any seats, I can sit wherever I want. The next person that gets on the bus can sit anywhere except for right next to me. Right? That's kind of how I view it. I'm sure you would too. All right, so nitrogen, oxygen, fluorine, and neon, they all kind of work the same way. We keep on adding 1 more electron to the p-shaped orbital. So with nitrogen, you can see there's 1 in each of these. And then with oxygen, I have no choice but to double up one of them, so that's fine. And that leaves 2 spaces to absorb electrons. Fluorine leaves 1, and then neon leaves none. So this is sort of how filling those orbitals works. And one of the things that I kind of want you to understand is that the quantum model will explain periodicity in a number of ways. But very early on at the beginning of the semester, one of the things that we had talked about is like, what on the periodic table, what does it mean when things are in the same column? Well, our common answer for that is, well, they have the same sort of way of behaving, so they have the same chemical properties. It turns out that everything here in this column, this 7A column, for these halogens, they all, if they gain one more electron, right? So fluorine right here, if it was to gain one more electron, it would have the same gas configuration as a noble gas neon, which means it's very stable. So gaining an electron represents an enormous stability. So fluorine will gain one electron and become fluoride. It does that very readily. Well, so does everything underneath it, chlorine, bromine, iodine, and astatine. And the reason for that is because each one of them, by gaining one more electron, will have a noble gas configuration after it does. And so when we say, what's the charge of everything in that column, we all say -1, and we're all right. The reason we're right is because they have space for one electron in that column. Okay? So the noble gases, they all fill their outer shells. The alkali metals, if they were all to lose one electron, right? If they got rid of this S-shaped, the electron that's here in this S orbital, if I go back here, if this one goes away, all that's left is this one, which is a noble gas configuration for helium. All right, so same thing with sodium. If one electron from sodium was to go away, it's going to be its outermost, and so what we're left with is the noble gas configuration of neon. Same thing for potassium and so on. So all these, if they lose just one electron, they're all in the same column, and we all say they get a +1 charge. They do so because doing that will give them a noble gas configuration. Alkali metals do the same thing. If they give up 2 electrons, they get the same kind of configuration as a noble gas. So the number of electrons that they can have the capacity to gain or lose kind of comes from quantum models. There are 8 spaces here in the second energy level, 2 here and then 6 here. And so that tells us really the number of electrons that need to be exchanged and where those electrons are going to be in S and P-shaped orbitals respectively. When you fill these orbitals, we only went up here to the second energy level, S's and P's. When we fill the third energy level, it goes 3 S's, 3 P's, 3 D's. And for the fourth energy level, it's 4 S's, 4 P's, 4 D's, and then up over here would be like 4 F's. What I want you to realize is that between the 3 P's and the 3 D's, which all these guys here are in the same energy level, the 4 S's kind of pop in the middle here. So one of the first principles is what's called the Aufbau principle. Electrons go to the lowest energy level orbital first, and they build up from there. So everything starts at the 1s orbitals, then it goes to the 2 S's and the 2 P's and so on. And then it goes to the 3 S's and then the 3 P's. And then when we get to the fourth energy level, it goes to the 4 S's first because they were lower in energy than the 3 D's. And the next slide will sort of show a periodic table where all of that is there. So you'll see like a 4s2, then the 3 Ds, and then we go back up to the 4 Ps, and then to the 5 S's, and then to the 4 Ds. So that's one rule that I want you to be aware of, Aufbau principle, things fill lower energy levels first. And the second one you need to be aware of is what's called Hund's rule, which is that the electrons fill empty degenerate orbitals first before doubling up, which is what we saw between nitrogen and oxygen. When oxygen gets another electron, one of these orbitals has to have 2 electrons. When nitrogen is there, every orbital has its own electron. So here's the periodic table in all its glory. So what they've done is they've left out all the filled energy levels, and they're just focusing on the ones that are not yet filled yet. So 2s1, 2s2, and then 2s1, 2p1, so going across, that's how you would see these. You get down here to the third energy level, 3s1, 3s2, 3s2, 3p1, 3s2, 3p2, and so on all the way across. Again, you're going to want to watch that video to see how these things get populated. When you get to the fourth energy level, remember, the 4 S's fill, and then the 3 D's fill. Okay, so it goes 4s1, 4s2, 4s2, 3d1, because these are the D's of the third energy level, 3d2, 3d4, 3d5, and so on. Right here at the fifth energy level, this would be 5s2, 4d1, so the D's are always one behind the S's. And then this goes back up when you go to the P's. So 5 S's, 4 D's, 5 P's. And then down here, cesium and barium, 6 S's, A 5D goes here, and then usually see that little break in the periodic table that says go to this other part here. And so we go down to this part here, and then the F's start. So F1, F2, F3, and so on. And then once we get to element 72, we come back up here and the D's start to populate. One of the things that I should point out is that with this, if I was to extend this arrow up and we would go to see 6 and 7, orbital levels get really close to each other. And they actually kind of start to overlap, which means that the places where we expect electrons to go when we're doing electron configurations and the places where they actually go can be a bit different. So in the video example, I do point out, take a look at copper right here. You would expect copper to be 4s2, 3d9, but in reality, we observe it to be 4s1, 3d10. And that's because this is a more stable configuration, and it also corresponds to the way that we actually see copper behave. So there are some exceptions to the way that we would commonly see this. This other one down here, praseodymium, is another example of where you would see that. So I tend not to ask questions about things that involve some of these. They might come up on homeworks, but generally speaking, I really do value your being able to do electron configuration for pretty much any atom on the periodic table, but doing so in the way that's expected. So I tend not to pick these ones just because they're tricky. I tend to pick other ones and stay away from those, but help you recognize that this model predicts one thing and what we observe is another. And there's another thing I want to point out. So, last slide had a periodic table. This slide has a periodic table. They both look like periodic tables to me. But there's one important difference. So here's element 55, 56. Next to it is 57, and then you go down for 58. On this periodic table, here's element 55, here's element 56, and then we go down for 57 as opposed to going down to 58. So the F ones start at lanthanum here, and then the D's start at lutetium. And that's different from this periodic table where we see the F1s, the D1s starting here and then going down to the Fs. So depending on the periodic table that you're using, you may actually come up with different answers than what a source might expect you to have. If this were a face-to-face class, this is the periodic table we would be using, and it's the one that I would probably encourage you to use when you're doing electron configurations. So I just want you to be aware of, and maybe even appreciate, when you see periodic tables, look to see how they break out these lanthanides and actinides. Because when they do, sometimes they start lanthanum and actinium up here, and sometimes they don't. And so it's a really neat thing to kind of pay attention to when you're looking at periodic tables. They are not all the same. And believe it or not, at least amongst academics, we're fun at parties, right? So at least amongst academics, there are some pretty heated debates as to if this is the right way to show the periodic table and which element should go where, and does hydrogen really belong here? So this, while it's a very easily recognizable icon, chemists are not necessarily done with the way that it's arranged. So it's still a living document. Okay, so let's get into periodicity. Periodicity is like the repetition of properties that we see in the periodic table that made it the wonderful map that it is. So some of the periodicity that we end up seeing comes from something called effective nuclear charge. And it gets the symbol Z. Nuclear charge always has the symbol Z, and so the effective Z is what we're talking about here. And what this is this corresponds to, for an atom like lithium, that's our example here. This electron out here, it's influenced by this nucleus, and just like these electrons are influenced by this nucleus. So lithium's got a 1s2, 2s1 electron configuration. There are 2 electrons in the first energy level, and then this third one's in the second energy level, which means it's further away. So this is a +3 nucleus. These 2 electrons that are closest to it shield it from this one. Okay, so this nucleus right here, it's got a +3 charge, but for this electron to see that +3 charge, it has to look through this cloud that's got 2 electrons in it. So this doesn't look like a +3 charge to that electron. It looks like a +1 charge. And so these 2 electrons here, they provide what's known as shielding. In this example, it's called penetration, basically meaning that this electron is in the same cloud as these other 2. This electron here feels the full attraction of this nucleus. Remember, nuclei are positive, electrons are negative, and so when this electron is closer to this nucleus, it feels the full attraction towards it. When this electron is kind of removed or further away from this nucleus, it feels less of an attraction. One, because there's a distance, and two, because there are negative things between it and that. I sometimes think about this like a concert. You know, the best view is up front. And if you're kind of a few human rows back, then you have to look over the heads of people in front of you. And if you are, my wife is 5'2", and that's a difficult thing for her at some of the concerts I like to go see. So she always likes to go up front, but I'm 6'2", so I know that I'm impeding the view of people behind me. I'm shielding them from what they want to see, which is the band and not the back of my head. So that's what this concept of shielding is. We don't actually calculate this all that much. We try to understand it. So the more shielding there is, the less positive the nucleus appears. So this Z right here represents the total number of positive charges in the nucleus. The shielding represents the number of electrons that are between that nucleus and the outermost electron. And the effective nuclear charge is the difference between those two things. So there are different kinds of electrons. There are things called core electrons, and there are things called valence electrons. The core electrons are the ones that are closest to the nucleus. They are not available for chemical reaction, which means that when this forms bonds, the core electrons are not the electrons you find in those bonds. And as you go across a period from left to right, that's what periods are, left to right, what they do is they provide shielding. Okay, so going back to this thing here, we are in the, this is for lithium, 1s2, 2s1. This 1s2, these two electrons right here, those are these two guys. They are what's considered the core electrons. So when this lithium atom reacts, these electrons stay put, and this is the one electron that would go away. This is a valence electron. This is the one that's available for reaction. These two electrons right here being in the core, they actually do provide shielding. Valence electrons do not. So they are furthest from the nucleus. They're available for chemical reactions. They increase as you go across the period. So you get more valence electrons as you go from left to right. So in the second column here, and in the second row, period, there's one valence electron here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, 8 here. Each of these has a 1s2 that comes before this 2 right here. So this would be 1s2, 2s1, 1s2, 2s2. That 1s2 stays the same as we go across. So the 1s2 is the core electrons. Core electrons do not increase from left to right across the periodic table. Valence electrons do. In this first column, there's 1. Here there's 2. Here there's 3, 4, 5, 6, 7, and 8. Okay? And the main thing to realize is that while those valence electrons are increasing from left to right across the periodic table, they're not providing any new shielding. Okay? And the really important thing for us to realize is the things that are in the same column on the periodic table, the main reason why they behave the same way chemically is because they have the same number of valence electrons in the same kinds of orbitals. And so if this wants to gain another electron, it'll do so in the p-shaped orbital, well, so will this. So I can expect these two guys to behave very similarly in a chemical fashion. So I've got a rather busy slide here. So the periodic trends going across the periodic table, when the effective nuclear charge increases, attraction of the outer electrons to the nucleus increases. Okay, and so when ZF decreases, the attraction to the outer electrons decreases. So what does that actually mean? As I go from left to right across the periodic table, my nucleus keeps getting bigger. All right, so here I have 3 protons, 4 protons, 5 protons, 6 protons. So the number of protons in my nucleus starts small, but then it gets bigger, 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 and bigger. So the nucleus gets bigger, and it gets more positive. The number of core electrons that are providing shielding is not increasing as we go from left to right. So that means that the valence electrons are becoming more and more aware of this positive thing in the center of the atom. It's getting more positive. Shielding is not increasing, and so these other electrons are more noticing of it. So the effective nuclear charge as we go across the periodic table increases, because as we go across the periodic table, we are increasing the number of protons, not increasing the number of core electrons, and so Zeph ends up going higher. So here's a number of protons is increasing, this is not, so Zeph increases. And the main way to sort of remember that is we keep getting new valence electrons, which do not provide shielding. We're not getting new core electrons, which do provide shielding. So there's no new shielding going from left to right, so our effective nuclear charge goes up. Going down the periodic table, every time we go down the periodic table, we're adding a new layer of core electrons. They just keep getting, the valence ones keep getting further and further away. And new levels of core electrons are popping up between them. So what that means is the effective nuclear charge goes down as we go down the periodic table. Here you see it increasing as you go up. Well, if it decreases going down, it must increase going up. So as we go down the periodic table, we are adding new core electrons, which means we're increasing shielding. So while we do also have an increase in the number of protons going down, we also have an increase in the amount of shielding, which means that our outermost electrons are further away. And that's what kind of brings reactivity to it. So lithium reacts pretty fast. Sodium, dangerously fast. Potassium, you can't even have out in the air. And I'm not sure people have actually had enough cesium or rubidium around to work with it safely. So there's a big impact on how these things end up working on a chemical level based on just this. And one of the things this influences is atomic radius. Now, atomic radius is the distance between the center of the nucleus and the outermost edge of the electron clouds. Okay, so that's the radius. And then, you know, if I was to go from one edge of the cloud to the edge of the cloud, that'd be a diameter. So we're just talking about the radius here. So as we go across the second period from elements 3 to 10, okay, so this would be lithium, beryllium, and so on, boron, carbon, nitrogen, oxygen, fluorine, and neon. So we go left to right. We notice that there is a downward trend in atomic radius. And it's not a linear trend, but it's downward. And so that means the atoms are getting smaller as we go from left to right across the periodic table. And the reason for that is because the nucleus keeps getting bigger and more positive, and it keeps drawing those electrons in. Remember, the distance we're looking at is from the nucleus to the edge of the electron cloud. So if this nucleus is getting more positive, this electron cloud is getting drawn in towards it, so it keeps getting smaller. So the nucleus is becoming more positive. We're not getting any new shielding. So going from left to right across the periodic table, we see a decrease. And this is just for the second period. If I was to plot this for the third period, you'd see the same decrease. Look at that, I did do it for the third period. So here's the third period, see the same decrease. Here's the second period, same decrease. But as I go down a column on the periodic table, there's an increasing trend. So going down a column here, this would be for lithium, this would be for sodium. Sodium is bigger than lithium. And the reason for that is because by adding another electron shell, that you know, here it's 2s2, 2p6. Now we have to go to the third energy level. So that's a whole new orbital, which is further away from the nucleus. And all of these guys, these electrons now are able to do shielding. And as a result, you know, I have a kid at the door here in just a second. So as a result, that electron shell is further away, and going down the periodic table, things tend to increase. Let me answer this real quick. You can't use it as you can turn them online, but use it as Sorry about that. Only one here. Well, the dog couldn't answer the door. The dog does not have opposable thumbs. So we have the electrons that are here. They're providing shielding. Now we get a new layer of electrons, and as a result, the pattern repeats. But as you go down the periodic table, things tend to get bigger. And so this is a nice graph because it shows you both trends. Going down the periodic table, things increase, and going across the periodic table, things decrease. So here it is showing over all 5 periods. As we get deeper into the periodic table, transition elements, they tend to go up and back down, so we get these little U's here. You are not responsible for being able to understand or explain those things. They're beyond the scope of this class. So I'd just say let's focus on some of the main group elements. So again, going down the periodic table, things get bigger. Going across the periodic table, things get smaller. Okay. Now, with respect to cations, when we lose one electron, we have the same number of protons, and so cations tend to be smaller than neutral atoms. And so here's the size of a lithium atom, and then here's the size of a lithium cation. It goes down by a little more than half. When beryllium is here, it loses 2 electrons, and it goes down a lot. And when we've got boron, it loses 3 electrons, it goes down by a lot. So we can see there's already a small trend going across. But as each one of these loses 1 electron, or 2 electrons, or 3 electrons, they get to be much, much smaller. So cations will be smaller than neutral atoms. But here's an example. If I've got neon, which has an electron configuration of 1s2, 2s2, 2p6, and sodium cation, which has the exact same electron, which one's going to end up being bigger in terms of its radius? So neon is going to end up being bigger because it has an equal number of protons and electrons. This is in the next row on the periodic table. So this is in the 3rd energy level. This is in the 2nd. However, there are more protons than electrons in this one, which means that those electrons are drawn into the atom just a little bit more, so that atom is going to be smaller. So because they have the same number of electrons, they're called isoelectronic, but sodium has more protons than neon does. So sodium plus would be smaller than neon. Otherwise, the trends that we had just talked about stay the same. Going down the periodic table, lithium cation is smaller than sodium cation, because going down the periodic table, things get bigger. K plus and Ca2 plus, those are also isoelectronic. They're going to have the same electron configurations. But Ca2 plus is going to have more protons in this nucleus than potassium would, which means that this would be smaller than potassium. Now for anions, where things have extra electrons, it's a reverse trend. So anions will gain 1 electron. And by gaining that extra electron, they have the same number of protons, but more electrons. And so oxygen here is a good example. So I've got, 8 protons in the nucleus here. And if I have just the normal 8 electrons as well, that's how big oxygen is. But if it gains 2 electrons, it gets to be this much bigger. Fluorine, again going across the periodic table, gets just a touch smaller. When it gains an electron, it gets bigger than its neutral atom, but it is smaller than the oxygen 2 minus anion. So anions tend to be larger than neutral atoms. And the same example, if I've got neon and fluoride, which have the same electron configurations, fluoride's going to end up being bigger than neon because they both have 10 electrons, but fluorine has fewer protons than neon does. So same number of electrons, neon has more protons than fluorine, which means that it's pulling the electrons a little closer in. Fluorine, or fluoride, I should say, has fewer protons than neon does. Questions on that before I carry on? The next thing that we'll talk about here is what's called ionization energy. And ionization energy is the energy that it takes to remove the most loosely held electron from a gas phase atom. So imagine I've got some atom here, it's in the gas phase, and I want to remove an electron, and that leaves this one positively charged. So that is the amount of energy that it takes. And generally speaking, going from left to right across the periodic table, that gets harder to do. So there's an increasing trend in ionization energy, going from left to right across the periodic table. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So it gets harder the closer you get to the right-hand side of the table. I want you to pay attention to these 2 dips. These are 2 exceptions here. It is easier to remove an electron from boron than it is beryllium. And you have to kind of ask yourself why. Once an electron is removed from boron, this is what's left, 1s2, 2s2. We take this electron away. We take the 5th electron away, so it's left with 4. And when we have that, the S-shaped orbitals are full in both the 1st and 2nd energy levels. That's pretty stable. So if we made something stable, it's going to take less energy to do, because when that electron is given up, it's more stable. Oxygen, when it loses an electron, the electron that it's going to lose is one of the ones that was in here in the P. So oxygen prior to losing an electron was 1s2, 2s2, 2p4. Once it loses an electron, it becomes 2p3. In the P3, you have 1 electron per orbital. In P4, you've got 2 in one orbital, and then 1 in each of the next one. So basically, it's 2 people are sharing a room, and another person has their own room, and another person has their own room. So the people in the 2 room and they're sharing a room, if they get to split up, that'd be fantastic. So one kind of goes off to college, the other one gets to stay in that room by themselves, and they're pretty happy about that. Okay, a whole bunch of people are going to probably experience the opposite this summer, this fall. Well, it's a bummer, isn't it? It really is. So 1s2, 2s2, 2p3 is the electron configuration of the ionized oxygen. And so we see that because we're forming something more stable, a half-full shell, it's a little easier for us to do that. The trend remains increasing from left to right. However, there is this noted deviation that we can kind of explain using quantum. So taking a second look at boron and oxygen, removing the electron from boron lowers the energy and leaves a full 2s shell. So here's the electron that's being taken away from boron, and this is what's going to remain, and this is stable. Same thing with oxygen. Here's what we have with oxygen so far, and when it remains, this electron right here, that's the one that's being removed. And so that leaves a half-full 2p orbital. So when this one's removed, the rest is half full. So if I drew this for the second and third period now, second period is exactly what I showed you. And I get up here to neon. And then for the next element, which is going to be sodium, there's a giant drop in its electron configuration. Not electron configuration, it's in its ionization energy. Why is there such a big drop? The reason there's such a big drop is because now all the electrons that are in the second energy level can provide shielding, which means that next electron is further away from the nucleus. The shielding has increased, so it's easier to remove. So that atom is bigger, the electron is further away. There are more electrons between that electron and the nucleus, providing shielding, so no one will really notice if we pick it off. And a good analogy for this is students who sit in the back of a class when they come into a college classroom. It's a great place to sit, I'm sure, because I'm not able to see that far with any real level of detail, so you think. There's a bunch of students from the first row to the second to last row that I have to see through in order to see the last row. So people tend to want to sit back there for that reason. The person in the last row can kind of take themselves out of class, and I may not notice. If you're closer to the nucleus, you're going to notice. If you're further from the nucleus, you're not going to notice. There's a lot of shielding between there, and that's the main reason why. So the reason that we see this trend going down the periodic table, so notice that ionization of neon is much harder than the ionization of argon over here. So this one's neon, this one's argon. The ionization of neon is much harder because there are fewer things providing shielding, whereas for argon, there are more things providing shielding. All of these electrons here provide shielding. Okay, so there's an increasing trend as we go across the table. Notice the exceptions, boron and oxygen, and then same sort of thing here, aluminum and sulfur. And then as you go, and then we have a decreasing radius. As you go down the periodic table from top to bottom, there's a decreasing trend, so from here to here. The reason for that is decreasing effective nuclear charge and increasing radius. And the last thing we talk about with this is what's known as successive ionization energy. So if I have an atom that likes to give off multiple electrons, like aluminum will form a +3 pretty readily, well, how does that work? So when aluminum goes to aluminum plus and 1 electron, loses 1 electron, this is its new electron configuration, neon 3s2. It costs us 1,577 kilojoules of energy. Okay? I take a second electron away. It costs me, I don't know why there are so many commas in this. I think it's the way Excel did it, they just comma to everything. But it's about 21,000, so it goes from 1,500 to 21,000. It's a big increase. Why is there such a big increase here? The reason for the big increase is because taking something negative away from something that's already positive is really hard. We have not increased the shielding, and so the electron is hard to get at. But when I take that second electron away, I've got a half full S-shaped shell left. And when I take another electron away, that's the one that's being removed. So now I have a noble gas configuration, and that corresponds to this one. So it's 32,000 kilojoules per mole to remove that. If I want to remove another electron, I've already removed 3, now I want to remove a 4th. I take that 4th electron away, now I've got aluminum plus 4, and that costs 411,578 kilojoules. That is a lot of energy. That is prohibitive. I do not have that much energy to pump into this to make that happen. So aluminum is, you're not going to find many things that have an aluminum plus 4 charge. The reason for that is because you have to dip down into the core electrons. So these ionizations here, they are pretty straightforward because they're successive and they're all using valence electrons. When I'm out of valence electrons after this ionization, then I have to take from the core. That's not happening. So that's the reason for seeing a curve that looks like this. Now, what we've gone through here, stop the share, is the bulk of chapter 9. Okay, so it starts, it starts with ionization electron configuration and where these things fit in terms of orbitals. And then I've pulled a lot of the things to look at in terms of ionization energy and atomic radius. The only thing I tend not to go over in this one is like the last 2 pages, which is metallic character, which is difficult to quantify, and something called electron affinity. So just to briefly mention it, electron affinity is the amount of energy that's given off when an atom gains an electron. So if an atom gains an electron, it gives off a little bit of energy. Woo! So it's woohoo energy, right? So it gives that energy because it got an electron. It got an electron because it's a species that wanted to gain an electron. So like fluorine becomes fluoride, it's super excited to do that. Okay, it gets reduced really, really easily. Metals, on the other hand, they don't really want an electron, they want to give it off. So the trend for that is kind of all over the place. Because there's no real trend, I will mention it like this, your book will mention it like that. If you're going to go on and do more materials chemistry, you'll spend some time on this subject, but it's one that we sort of introduce here so that you can remember that it'll come up again later. It's not something that we just want to dismiss offhand. It's just nothing that we're not going to go into the same level of detail. So that takes us through the 9th chapter. Let me talk briefly about where the class goes from here. So next week is week 9, which is the last week before our end of semester, our final test. And basically what we're doing is we started with quantum to see how atoms build up. And then with quantum, we figured out where the electrons in atoms go. Next week, we're going to look at how 2 different atoms would come together to form a bond, where those electrons go in bonds. And because we're going to spend time on bonds, we're looking at molecules. After that, so that's going to be like Tuesday of next week. Thursday of next week, we'll start to look at the shape of those molecules when they form those bonds. The shape of those molecules will inform the way they behave, so the behavior based on that shape. So there's this really nice arc. We're going from electrons and atoms to bonds, bonds to shapes, shapes to properties. And we're going to end at properties. And for those of you that are going to go on into biomedical stuff, biochemistry, organic chemistry, and whatnot, the shapes of molecules has a huge influence on the way that they end up behaving in living and non-living systems. So that's a really important thing to pay attention to. For those of you that see yourself on that path, this is like a really formative thing for the class. So I want to make sure that you're dedicating time and resources. And again, I've mentioned this in the emails, and for those of you that are here with me each time we do class, thank you so much. It's so nice to not be talking to just a picture of myself. So thank you so much for coming. But for those of you that are doing this, reading along is so important. This is the stuff that's just, you can't just do with math, and you can't just Google and try and pick up piecewise. If you really want to know this stuff, reading along is a very important thing to do. So I hope you are doing that. All right, that takes us to the end of what I had laid out for us today. Don't forget your quiz closes at 2 o'clock tomorrow, and your extra credit due tomorrow at midnight, or by midnight, and then also homework due by midnight on Sunday. We'll see new stuff next week, your last quiz next week, and then the week after that will be the last of the exams. Questions, concerns, violent objections? You all okay? All right, well, stay safe. I hope everything's going well, and let me know if you have any questions on anything else, okay? So take care. Bye-bye. Oh, there are 2 things in the chat. Thank you, and thank you. Have a great day. Good. Take care. Bye, guys.